Well, I start recording. You can see the presentation on the screen, and the topic of this lesson and the lesson on the next week is interpolation and polynomial approximation. Here we see the agenda of the lecture, problem statement, and we consider two types of interpolating polynomial: Lagrange polynomial and Interpolation. The problem statement is presented here on this slide. Suppose that we have a table where some data is represented. This data, it may be, for example, the number of people in some country or something else. Here in this table, you can see the population in United States of America. That was fixed in 1940, 1950, 1960, and so on. So this table lists the population in thousands of people. And the question is, can we provide a reasonable estimate of population in some other year? For example, 1955 or 1995. Of course, this data is old. Now, situation is different, but the idea is the same. We have a table. We know the values of some function only in the number of given points, and we want to predict the value of a function at some other point. The predictions of this type can be obtained by using a function that fits the given data. This process is called interpolation. We consider on the first lesson that one of the most useful and well-known classes of functions is a class of polynomials. I can write, for example, a polynomial of the first degree. Polynomial of the first degree is just a line and the general form of a polynomial of the first degree can be written as e1 of x equals to x0 plus a1x. This is a polynomial of the first degree. And I close the presentation for a minute. then other students will see the board. This is a polynomial of the third degree. How to write polynomial of the second degree? In general, E2 equals to A0 plus A1x plus A2x squared. This is a polynomial of the second degree. Polynomial of degree n can be written as A0 plus A1x plus and so on, an x power n. This is a general form of polynomial. And this form is written in my presentation. This form is written in my presentation. Pn equals to A0 plus A1x plus and so on, an x power n. How many coefficients are there in a polynomial of degree n? N plus 1 coefficients. A0, A1, and so on. In polynomial of degree 1, 2 coefficients. Polynomial of degree 2, 3 coefficients, and so on. To write a polynomial, I should fix these coefficients. If somebody tell me these coefficients, I can write a polynomial. And one of the reasons why the polynomials are very important is that, first of all, these polynomials are very simple. It's very simple to write this polynomial. And for any given function, for any given continuous function, there exists a polynomial that is close to the function as desired. For any function, you tell me the function, and I can tell you the polynomial. Polynomial that will be close to this function. And this statement is written here in the form of so-called Weierstrass approximation theorem. Suppose that f of x is defined and continuous on the interval ab. Then, for each epsilon greater than 0, there exists a polynomial p of x with the property that f of x minus p of x smaller than epsilon for all x between a and b. This theorem is illustrated here on this slide. You may see here the graph of the function, this line. This line corresponds to the graph of the function. This line corresponds to the polynomial. And you can see that the polynomial p of x lies somewhere near this function, between upper bound and lower bound. Lower bound is f of x minus epsilon, and upper bound is f of x plus epsilon. These two lines correspond to the f of x plus minus epsilon. And between this upper and lower bound, there exists a polynomial. So I can find a polynomial that will be very, very close to any function that I want. Yes, maximum. I can take it, for example, 0.1, or I can take it 0.01. It will be closer, and so on. But this statement is just a theoretical statement. But the question is how to find this polynomial on practice. How to find it. And we consider two techniques how to find this polynomial. I come back here to this picture, and again I close the presentation. I write some explanation on the board. For example, we can consider any function. Suppose it can be, for example, exponential function f of x equals e power x. It will look like this. Exponential function. In the point 0, the value is 1, and it looks like this. This is y, this is x, 0 and 1. It doesn't look like a polynomial, but if I select some interval, for example, from 0 to 2, and on this interval, I can find a polynomial, some particular polynomial that will be close to this function. And the difference between the values of polynomial and the values of the function will be smaller than epsilon, smaller than the some given number. Okay, and share the presentation again. Well, the simplest case, let's consider the linear interpolation problem. Linear interpolation means that we are going to find a linear polynomial of the first degree, polynomial that passes through given points. Before we consider this problem, and my question is, suppose that we have three different points. Are there any polynomial of the first degree that can pass through three different points? What can you say? Are there any line that pass through three different points? Line that pass through 3 points. Suppose, my question is, suppose that we have 3 points, 3 different points. Can we draw a line that pass through 3 points?
So it depends if the points are aligned or not.
Of course, of course. In general, we cannot draw a line, of course. Because if this point looks like this, 1, 2, 3, no line pass through these points. That's why we consider just 2 points. We consider 2 points, and we are going to find a polynomial of the first degree that pass through these 2 points. So suppose that we have 2 points. I denote it here as x0, y0, x1, y1. The values of the function f of x0 equals to y0, f of x1 equals to y1, and we try to approximate the function f by means of the first degree polynomial. First degree polynomial that pass through these 2 points. First, we write the so-called auxiliary functions L0 of x and L1 of x. You can see that L0 doesn't depend on f of x. It depends only on x0, x1, and x, but x0 and x1 are constants. It's some fixed numbers. And L1 is the same. It depends only on x. x0 and x1 are constants. And after that, we can write a polynomial p of x in the following form: L0 of x times f of x plus L1 of x times f of x1. Yes, this is. Let's prove that this polynomial will be interpolating polynomial. Let's prove it. So the proof is written here. The proof is written here, but I reproduce it on the board. I reproduce it on the board, and again I switch from the presentation to the video. Let's reproduce the proof. What we have? We have a polynomial we have a polynomial p of x that equals to x minus x1 over x0 minus x1, x minus x1 over x0 minus x1 times f of x0 plus x minus x0 over x1 minus x0 times f of x1. This is a polynomial. I just write it in a full form. It was written in my presentation also. Let's substitute the point x0 here. And let's try to compute p of x0. What will we have? What will we get? If I substitute here x0, I get 1.
It will be f of x0 plus 0.
F of x0 plus 0. So the value of the polynomial at the point x0 equals to f of x0. And the value of the polynomial at the point x1, if I substitute x1, it will be f of x1. F of x1. Which I can say that the polynomial agree with the function at the points x0 and x1. It passes through the same points. Well, exactly the same is written here in my presentation, that p of x0 equals to f of x0, p of x1 equals to f of x1. And p is a unique linear polynomial passing through two different points, x0, y0 and x1, y1. The picture that illustrates this statement is here on the slide. We have the point x0, y0. We have the points x1, y1. This is a graph of the function. Function can be non-linear, any continuous function that pass through the points x0 and x1, and the polynomial of the first degree y equals to p of x. This polynomial passes through these 2 points. It's a line, yes? And I can say that this line interpolates the data between x0 and x1. How to get interpolation between x0? I can draw a line and take the point here, the point from the line. You can see that this line is the same, only at the boundary points. Between, it can be a difference. Well, to understand how it works, let's solve the exercise. Let's solve some exercise. I open, yeah. Let's consider this table of values. I corresponds to the number of points 0, 1, 2, 3. X, it's a point x. F, it's a function value. And let's consider first 2 points from this table. x0 equals to 0. x1 equals 2. And f0 equals to 1. And fi. And f1 equals to 3. I consider the first 2 points. Those 2 points from this table. The task is apply the formula and find the polynomial that interpolates this function. Find the first degree polynomial. Well, 10 minutes for you to find this polynomial. Well, next time, if you want to come here to the lesson, you must take paper and pen. It's very strange that you are student on the third course and you don't know that you should come for the lessons with pen and paper. You can solve, of course, you can solve it on your laptop, but I don't know how. You can write the solution in your laptop. Try to do it. Well, do you understand the task? The initial information is written here in first two columns of this table, 0, 2, 1, 3, and I ask you to write, and also I reproduce this data on a board. I ask you to find the first order interpolating polynomial. I ask you to find first degree interpolating polynomial. The information is written here. Apply this formula and find their interpolating polynomial. Try to do it yourself, and after 10 minutes I show you the correct solution. Well, you have 10 minutes to solve this problem. I come here. Well, did you solve this problem? You can write your solutions in chat because polynomial is more or less simple. Did you solve it? Why you use E?
Exponential, because I was just like,
Exponential is an example. Exponential function is an example.
Then it's x plus 1.
It's just an example. The values of the function are 1 and 3 at the points 0 and 2. We have 2 points, 0 and 2, and the value of the function x plus 1. Right. X plus 1. The solution to this problem is x plus 1. We should substitute x1 equals to 2, x0 equals to 0, here, and find the solution, x plus 1. And in this problem, is very simple to check, is this solution correct or not? I should substitute these points. If I substitute 0, I get 1. If I substitute 2, I get 3. So the solution is correct. And very quickly, I ask you to solve the next problem. Let's consider another 2 points, these 2 points. 2, 3, 3, 2. Let's consider another 2 points. 2, 3, 3, 2. Now let's consider these points. And let's find a polynomial of degree 1 that pass through these 2 points. 2, 3, 3, 2. What will be x1 here? For this data, x1 is 3, x0 is 2, and so on. So the answer for the first problem is x plus 1. The answer for the second problem, let's try to find it. X1 equals to 3. Sorry. Yes, x1. X minus 3 over 2 minus 3 times 3, because f of x0 equals to 3, plus x minus 2 over 3 minus 2 times 2. Very simple task to simplify this formula. There is plus or minus 1 in denominator, and it's very simple to find the solution. Did you find it? Minus x plus 5. Your solution is minus x plus 5. I don't know is it correct or not, but it's very simple to check. If we substitute 2, the answer should be 3. Yes, 3. If we substitute 3, the answer.
Yes, sir. Minus x plus 5.
What? Sorry.
Minus x plus 5.
Yes, minus x plus 5. Minus x plus
yes,
5.
Please.
It's a correct solution.
Please, sir.
Yes.
Yeah. I didn't use your formula because I don't really understand interpolation of Lagrange, but I use just like the method that we use when we were in high school. So
okay. Well,
it's just
your method is correct, but you can use it only for 2 points. And
exactly.
I think you cannot use it for 3 points. And the next task, the next problem that we consider is how to find the interpolating polynomial of degree 2 that pass through 3 points. 3 points. Yeah. So let's consider these points all together. Let's consider these 3 points all together. And the question is how to find the interpolating polynomial of degree 2. I again share the presentation. Well, this picture corresponds to the linear interpolating, and linear function. It's very easy to find, but in general, the interpolating problem can be formulated as follows. We have n plus 1 points. N can be 2. In this case, we have 3 points. There is a function f of x. We know the values of a function f0 of x, f1 of x, sorry, f of x0, f of x1. We know the points x0, x1, so we know n plus 1 points. And the problem is to find a polynomial that pass through these n plus 1 points. In other case, I can reformulate this problem as follows. We are given a table of n plus 1 data points, x0, y0, x1, y1, and so on, xn, yn, and we seek a polynomial of a lowest possible degree for which p of xi equals to yi for all I from 0 to n. Such polynomial is said to interpolate the data. And this polynomial is called interpolating polynomial. And there is a theorem. I'll give you this theorem without proof. Proof is written here, but I skip it this lesson. If x0, x1, xn are distinct real numbers, then for arbitrary values y0, y1, yn, there is a unique polynomial Pn of x of degree at most n, such that P of xi equals to yi. So this theorem tells us that for any given data, if the points x0, x1, xn are distinct, then there exists unique polynomial that pass through these points. So this is a proof. This lesson I skip this proof. Maybe we come back to this proof next week and discuss about it.
Yeah, please, sir.
And now I want to explain how we can write a Lagrange interpolation polynomial. How we can write a polynomial that interpolates the data. The idea is the same. We can write a polynomial p n of x that equals to sum of the following terms: f of x0 times ln or L0 of x plus and so on f of xn ln of x, where lk of x is a fraction that looks like this. Here it's written as differences, x minus x0, x minus x1. The point k is skipped. You see that here is written x minus xk minus 1 times x minus xk plus 1, and so on. And here the terms xk minus x0, xk minus x1, and so on, xk minus xk minus 1, xk minus xk plus 1, and so on. Well, when n equals to 1, we have only the first terms of this fraction. And these first terms corresponds to x minus x1 over x0 minus x1. This is the first x minus x1 over x0 minus x1, and x minus x0 over x1 minus x0. The polynomial of the first degree is a partial case of polynomial of second degree. Well, I think it's hard to understand this formula for the polynomial of degree n. And now I write on a board the particular case of this formula for the degree 2. I close the presentation, I switch to the video, and I write on the board the formula for the polynomial of degree 2. Well, we have 3 points: x0, x1, x2. We have 3 values: y0, y1, y2. The polynomial is written in the following form: p2 of x equals to y0 times L0 of x plus y1 times L1 of x plus y2 times L2 of x. The general form is more or less the same as for polynomial of degree 1, but the polynomials L0, L1, and L2 a little bit complex in comparison with the polynomial of degree 1. How to write polynomial L0? L0 of x equals to x minus x1 times x minus x2 over x0 minus x1, x0 minus x2. The polynomial L0 of x is organized in such a way that L0 of x0 equals to 1. L0 of x1 equals to 0, because here we have x1 minus x1 equals to 0. X0 of x2 equals to 0, 2. I write it here that L0 of x0 equals to 1, L0 of x1 equals to 0, L0 of x2 equals to 0. How to write L1? L1 of x equals to x minus x0. I should skip the point x1. Here I skip the point x0 when I write x0, L0. Now I skip the point x1, x minus x2, and L1 minus x0 times x1 minus x2. And the last term, L2, I should skip the point x2. X minus x0, x minus x1 over x2 minus x0, x2 minus x1. Three terms, L0, L1, L2. If I find these three auxiliary polynomials, I can substitute it in this formula and find their result. The polynomial of degree 2, that will be interpolating polynomial that interpolates the given data. I don't know, will we have time for this? We have just 10 minutes, so today we have only one lesson. I think we start, and I ask you to finish this computation at home. Suppose that we want to solve this problem. We want to find a polynomial of degree 2 that interpolates this data. What we should do? To write L0 of x first. What is the value of x1?
x1,
2. And we have x minus 2, x minus x2, x minus 3 over
minus 2 and minus 3.
Yes, the difference is over minus 2 times minus 3. That's all. L0. The next, L1. L1, you should substitute these points. L2, you should substitute these points. And after that, we have polynomial P2 of x equals to L0 times 1. L1. For L1, the equation will be simple because x0 equals to 0, minus 0. Well, you should substitute, and L0 of x times 1 plus L1 x times 3 plus L2 x times 2. I think it's not a problem. You should carefully write L1, L2, substitute into this formula, simplify it, and as a last result, as a final result, you should get polynomial of degree 2. What is polynomial of degree 2? Polynomial of degree 2 is defined by its coefficients. A0 plus x, A0 plus A1x plus A2x squared. You should find three numbers, A0, A1, and A2. And write the polynomial. And when you write it, it will be very simple to check. Is it correct or not? You should substitute 0 and you get 1. You should substitute 2 and you get 3. You should substitute 3 and get 2. I ask you to finish these computations at home as a home task. Write a polynomial of degree 2 that interpolates this data. Write a polynomial of degree 2 that interpolates this data. And next week we continue from this point. We discuss about the error of interpolation. Because to write an interpolating polynomial, it's not the end. Because when you write it, the question is, what is the difference between interpolating polynomial and a function that this polynomial interpolates? Because this difference may be very, very large, or maybe small. There is a theorem that gives us an upper bound of the error. Upper bound for the difference between the function value and the value of interpolating polynomial. Well, please, any questions? Okay, if you don't have any questions, later, maybe this day, maybe tomorrow, I will send you the video, I will send you the presentation. And for the next week we continue. We discuss about the error. We consider another interpolating polynomial, Newton polynomial, another type of interpolation. And if you don't have questions, let's finish our lesson.